Alright guys, let's get to it. We're about to look at some physics review here for Unit 4. Okay, so we have particle moves along the x-axis with its position given by. At what time is the particle at rest? So with this physics stuff, again, the vocab is like really important. We know that at rest means velocity equals 0. So I know that the velocity is derivative of the position. Okay, so if I take the derivative of this, 6t squared minus 42t plus 72, that goes away, equals 0, and I need to solve that. I'm going to factor out a 6. Really hope these all divide by 6. Let's see, 42 divided by 6 is 7. 72 divided by 6, is it 12? I believe that's 12. Okay, and then I continue factoring this. T minus 3, t minus 4. And so at time 3 and time 4, the particle is at rest. It's greater than or equal to 0, and those are both greater than or equal to 0. Or that. Okay? All right, perfect. Let's see. The position, particle, the x-axis is blank. Okay, when t equals pi, what is the acceleration? Okay, cool. So if that's position, velocity, okay, derivative of sine is cosine 2t times 2. The derivative of cosine is negative sine 3t times 3. So the negative goes to positive. Now for acceleration, okay, the 2 is still here. The derivative of cosine is negative sine 2t times another 2, right? And then the 3 is still here. Derivative of sine is cosine 3t times another 3. So here's what I get. Negative 4 plus 9. Okay, so there's my acceleration. So I had to do two derivatives, being really careful about the sine and cosine, positive and negatives, right? So now, if I want to find acceleration at pi, okay, well, 2 times pi is 2 pi. 3 times pi is 3 pi. Now, let's remember, all right, on my unit circle, this goes 1, 0, 0, 1, negative 1, 0, 0, negative 1. And remember how it goes sine, nope, cosine, comma, sine. Cosine is the x coordinate, okay? Sine's the y coordinate. So at 2 pi, that's all the way around, sine is 0. So this is going to be negative 4 times 0. Okay, at 3 pi is around once and halfway back around again. Cosine is negative 1. All right, so this gives me 0 plus negative 9. So I'm going to get negative 9 for my acceleration. Okay. Okay, perfect, you guys. This is a very good example of L'Hopital's. Because remember, when we have numerical limits, the first thing we always do is well, the sine of 0 times the cosine of 0 over 0. The sine of 0 is 0. I can use the same chart again, right? Sine 0 is 0. Cosine of 0 is 1, and I get 0 over 0. Now, when I do L'Hopital, when I take the derivative of the top, you guys, I'm going to have to do a product rule, okay? Product rule goes like this. Derivative of the first times the second plus the first times derivative of the second. And then on the bottom, the derivative of x is 1. Remember with L'Hopital's, you're not doing the whole quotient rule thing. You're just taking the derivative of each part separately. Okay, now when I plug in 0, so now I'm going to go ahead and put this in. I get cosine of 0 times cosine of 0. I get sine of 0 times negative sine of 0 over 1. Okay, you guys, well, check it out. The cosine of 0 is 1, so I get 1 times 1. The sine of 0 is 0. So I get 1 over 1, which is 1. Okay? All right, so that's just a good L'Hopital's rule for you right there. Ooh, hello. Okay, so we got a guy walking away from a street lamp at a rate of blah blah blah. What's the rate at the person's shadow is decreasing? Okay, you guys remember that triangle problems? Like usually with like I don't know, a guy walking away from a ladder or a triangle or a ladder falling down a building, a guy walking away from a lamppost, right? Or like volume and like water dripping out. All those type of stuff, we got to remember related rates, okay? All right, this is kind of a weird related rate question, but when I see this, I know I'm working with triangles, but what I want to do is I want to actually make these similar triangles right here. You guys see those two similar triangles because they're both right angles? Okay. A person whose height is 6 is walking away from the base of a streetlight along a path at a rate of, he's going this way, 4 feet per second. The height of the streetlight is 15. What is the rate at which the shadow is lengthening? Okay, let's see here. Okay, so the height is 6 feet walking away at a rate of 4 feet per second. What is the rate at which the shadow is lengthening? Actually, I think I want to bring this walking at 4 feet per second. Okay. Okay, you guys, I'm going to go ahead and I was working this out, but I did it wrong. So let me, got to come back to here. Okay, so I called this little section Y, but that actually doesn't, well, actually, first I tried to make this whole thing Y, and then that was messing with me. I'm going to make this little section Y. Now, check it out. In similar triangles, which we know these are similar triangles, they have sides that are proportional. So I was trying to find a proportion for like 15 over 6, right? Okay, so check this out. So 15 is the big side of that, 6 is that, and then this will be the base, which is actually x plus y over the base of that, which is just x. I think that's where I was going wrong before, was I was using y instead of x plus y. Okay? Now, so that's my equation that I'm going to base everything off of. Now, before I start taking derivatives, because, man, I do not want to do a quotient rule with this. That would be really ugly. I'm going to cross multiply this, okay? I'm going to get, so I have this equation, 15x equals 6x plus 6y. And if I subtract this 6x to the other side, I get 9x plus 6y. So that is the portion that I'm going to work. All right. Now I'm going to take the derivative of both of these with respect to time. The derivative of x is 1 dx dt. The derivative of y is 1 dy dt. I'm going to look at what I have, okay? Now over here, he is walking, so y is changing at a rate of 4 feet per second. So that is actually dy dt. So I'm going to go and call that 4. And then we're going to see what's happening with the shadow. Okay, so 9 dx dt equals 24. So then that equals 24 divided by 9. Put it in decimals, which is a little annoying. Let me reduce this by 3. If I reduce this by 3, that's 8 thirds, which I know 3 goes into 8 two times. That's 2 and 2 thirds. Then that's going to give me 2 and 2 thirds right here. Okay, little tricky. We're not really used to doing the similar triangle with rates of change. We're more used to doing Pythagorean theorem or, all right, let's take a look at number 5. Okay, cool. We like these. The approximation ones, you guys. Um, line tangent to the graph, all that, right? We're going to start by writing the equation of the tangent. Okay. Now, this is at x equals 2. And we're looking for, okay, so at x equals 2, the y coordinate is going to be what? Well, it gives it to me right there. The y coordinate is going to be 1. And what's the slope going to be at x equals 2? All right, well, the slope is going to be the derivative at that point, is 4. So here's my equation. Y minus 1 equals 4x minus 2. Now, what you do with these approximations is I'm going to like basically guess what that is because I don't know what the equation is, but I have a really nice line, right? So it's kind of like if I have this. So you guys, like if this is 2, then I'm going to approximate at 1.9. So it's not the point on the curve, like I'm looking for that. I'm approximating it down here, but it's like close enough, right? I'm going to go ahead and plug in 1.9. So let's see what we get. We get y minus 1 is 4. And then 1.9 minus 2 is like negative 0.1. These are usually on the no calculator section, so you got to do a little bit of decimally stuff, but that's fine, right? 4 times negative 0.1 is negative 0.4. And then I add the 1 over. So 1 minus 0.4 is 0.6. So that is going to be my approximation. Okay? All right, cool. Here's another rate of change one. The radius of a circle is increasing at a rate of 0.2. That's a radius. I'll go and use dRdt for that. What is the rate of increase in the area? So I'm looking for dA dt at the instant when the circumference is 25. Okay? This is interesting. Now, you guys, there's a few different things going on here, but I'm looking for an area, so I should probably get an area formula, right? And with the circle, we know the area is pi r squared. So dA dt is pi. The derivative of 2r of r squared is 2r dr dt. And I can start plugging stuff in, right? I can plug in dr dt. I'm going to plug that in right here. I'm looking for dA dt. So the only thing I need left is r. So how am I going to find that? Well, check it out. They gave me some information over here. They told me the circumference was 20 pi, and I know that the circumference of a circle is 2 pi r. So that tells me that the radius is 10, and now I have that. Okay? So now I've got all my information. I can find dA dt is pi 2 times 10, and dr dt is 0.2. So that's 20 times 0.2. 20 times 0.2, so 20 times 2 is 40, and if I move the decimal over, is 4, so that's going to equal 4 pi. Oh, that's rude. They really wanted to make sure I knew how to do that decimal thing. Okay, 4 pi. There we go. Okay, now, do we have, is this our free response stuff? Yes. And there's this equation missing every once in a while when you take a computer problem and you turn it into a worksheet. Weird things happen, so let me go figure out what that equation is. 1 second. Okay, well, fortunately, or unfortunately, I don't know, whichever way you guys think about it, I can't find what that equation was supposed to be, and I can kind of read it from here. It had to be something about, actually, I have no idea. So we're not going to be able to do that part, but I think we can do this part. So let's take a look. Karen rides a bicycle along a straight road from home to school, starting at time and arriving at school t equals 12 minutes. During that time, her velocity is modeled by the piecewise function. Let's talk about this, you guys. When her velocity is 0, she is at rest. I just want you to understand this graph a little bit, right? Here she's at rest. Here she's at rest. Otherwise, she's biking, okay? Let's kind of tell a story here. Here is what my friend Karen is doing. Karen starts riding this, and she's accelerating. She's getting faster and faster. And she has a thought. Wait a second, I forgot my math book at home. And then she starts decelerating down to there. So she stops her bike. So she's stopping. She looks in her backpack. Shoot, I did leave my math book at home. Karen turns around, goes back to her house, okay, grabs her math book, starts going again. It's back to the same spot where she is. She's sitting at a stoplight, maybe. And now she's getting faster, faster, faster going to school. This does not mean she's at rest. This means she's constant. She's not accelerating, great speed. She's going. And then, she decides to slow down a little bit. Ooh, I was going a little too fast there. And then she's going. And then as she approaches the school, she slows down and stops. Okay? You gotta be able to kind of interpret it. So that's a little story I'm doing. find the acceleration at 7.5. Now, if this is velocity, we know that acceleration is the derivative of velocity. Well, the derivative is just the slope. So what's her slope right there? Now, don't just look at this and go, oh, down 1 over 1, it's -1. You got to be a little bit more careful than that with this. Okay, we got to go like this. Down, it's actually going down 0.1 over 1. So her acceleration at 7.5 is -1. Now, velocity, miles per minute. So this is going to be miles per minute squared, right? And then that's kind of all we can do because we don't have this second part of it. Okay, so what I was saying, we got to ignore number 8 because I don't really have a equation there to work with. So that's all right, you guys. We're just going to go ahead and skip equation number 8. Okay, but let's go ahead and look at number 9. I think we can do this one. This is our last one. Oh, no, we don't. Okay, the rate at which people enter a given amusement park on a given day is enter. The rate at which they leave is leave. They're measured in people per hour, and time is measured in hours after midnight. So time 0 is midnight. These functions are valid from 9 to 23, so that's like 9 a.m. and 11 p.m., I guess. At time equals 9, there are no people in the park. Cool. Okay, let h of t, from 9 to t, e minus l, blah, blah, blah. The value of h of 17 to the nearest whole number is 3725. So that means that the number of people entering plus the number of people leaving, that's about where it is at that point, okay? Find h prime of 17 and explain the meaning of both of these. All right. So h prime of t is going to be the derivative of this. And we know that the derivative of integral is going to be e, and I put that in, of t minus l, I put that in, of t. Okay? This is definitely a calculator question. So h prime of 17 is going to be e of 17 minus l of 7. All right, so that's just kind of like the at time 17, how many people are entering, how many people are leaving. Okay? All right, I'm going to bring up my calculator here. Okay? And we're going to go into y equals, here all the stuff here. I'll go ahead and put the entering equation up here. Divided by, and then it's x squared minus 24x plus 160. Okay, and then I'll go ahead and put the leaving equation here, 9890 divided by parentheses. And then this one is going to be x squared minus 38x plus 370. All right, so there's my entering equation. There's my leaving equation. You guys remember I taught you that you can do this from the graph, but you can also just do it from out here. If we figure out what alpha trace y1 at 17, that'll just plug 17 into my first value. So that's e of 17 is going to be 380.487. And then if I do y2 at 17, is going to evaluate that for me. That's going to be 760.769. And then I can kind of go up here and go that minus, so I don't have to retype them all in, that equal. So h prime of 17 is negative 380.281. Okay? Now, I kind of jotted all that down. So let's see what this is talking about. Well, remember when we're talking about an integral, it's like the number of people that are coming in. So what this is saying is h of 17. Let's see, these are people per hour. And if I go backwards one step, it's people. That's how many people in the park at time equals 17. Okay, since 0 is midnight, what is that? Dude, I'm the worst at military time. Let's see. 12 would be noon at 5 p.m. There's that many people in the park. What does H prime of T represent? So that's people per hour. It means that 380.281, we'll say 380 people per hour are leaving. Basically, because it's negative, like more people are leaving than are coming. Okay? All right. And cool, cool. That's it for that one. Great. Okay. So here's our last one. We definitely love these. We know that this is a big rate of change question. Let's see if we can make our way through this. Water's draining from a conical tank with a height of 12, diameter of 8. All my information is in there. Into a cylindrical tank that has a base area 400 pi square feet. The depth of water in the conical tank, H, is changing at a rate of, so dH dt is H minus 12 feet per minute. Okay, the volume of a cone, so let me do the cone up here. 1/3 pi r squared H. Okay, great. Let Y be the depth of the water in the cylindrical tank. At what rate is Y changing? Okay, so this is Y, and so I'm looking for dy dt equals what when H equals 3 up there. Woo, there's a lot going on here. Let's see if we can make our way through this, you guys. All right. Remember that anytime we're using a cone, okay, we talked about this a long time ago. What's happening as it's going down is the radius and the height are both changing, right? So like when the cone is completely full, let's look at this one that's completely full. When it's completely full, the radius is 4 and the height is 12, okay? Now, as it starts emptying, both R and H are changing. Both of them, okay? If you're looking at something like this, the radius never changes, only the height changes. But over here, they're both changing. You have to do this little thing off on the side, you guys, where you go, okay, the 4 to 12 radius to height equals R to H. Cross multiply that. So 4H R, and I'm going to solve for one or the other. Now look, in order to solve, it gave me dHdt, so I really want to work with H. I don't want to work with R. But if I solve this, if H is 3, all right, I'm going to go ahead and take that. Nope, just did it wrong. I solved for H, which will give it to me in R. I want to solve for R, which will give it to me in H. Ah, for goodness sakes. Okay, let's try that again. I'm going to divide by 12. So R is H. That's what I'm going to put in over here. Now let me work with this for 1 second. R is H over 3. Okay. So it's 1/3 pi H squared over 9 times H. I'm definitely going to simplify this first. I do not want to work with it like this. 1/3 pi H to the third. And actually, I should have combined that 3 and that 9. I should have gone 1/27. Okay. Now I can figure out how quickly the volume of that is changing, which is basically telling me how much water is going down, how much water is dripping down, okay? Check it out. dV dt is, that's a constant, 3h squared dH dt, all right? Okay, I've got dH dt. Now, do I have h somewhere in the problem? We'll go look down here at what, let y be the depth, what rate is y changing when h is 3? So this is the important thing I need to work with. It's telling me h is 3, okay? Check it out. If h is 3, the rate is -9. And h is 3, and we can plug those things in. So dV dt is 1/27 pi, 3 times 3 squared, -9. That's 1/27 pi. 3 times 3 squared is 27. -9. 27s cancel out. So this is dripping out of that one at a rate of -9 pi. And it's like volume. So I don't know if we necessarily need this, but like feet cubed per minute. Okay, now if it's coming out of the top one at -9 pi feet, guess what? Entering this one at positive cube. Okay, makes sense? It's draining out of one, it's filling up the other one. Okay, so positive 9 pi. Now, guys, the formula for a cylinder, all right, like a soup can, it didn't really give us that, but it's basically the formula for a cylinder is the area of the base times the height. So it's this whole area, which is a circle, times the height, okay? So this cylinder is, or the volume of the cylinder, I should say. Now, it didn't tell me what the radius is, but it actually gave me this entire pi r squared, didn't it? It told me pi r squared is 400 pi. I don't need to find the radius. The radius would be 20 and then put it back in there, right? But it told me the area of the base, and the area of the base was 400 pi times h. So the dV dt for the cylinder, I'm just going to put cylinder right here, is 400 pi dh dt. Okay? Oh, but I'm using h as if it were that. H, and Ember told me to change it to Y, so that's my bad. I'm just like writing. I'm writing height because it is the height, but they wanted me to call it Y. So let me go back. Y. I had to go, not too bad. And it wants me to find dy dt. So I'm like right there. But what's dv dt? Well, how fast is this cylinder filling up? It's filling up at a rate of 9 pi because that's what it's dripping out of the other one. It's like a really multi-part problem. So 9 pi is 400 pi dy dt. If I divide both sides by 400 pi, okay, dy dt is 9 over 400. Now, this is just a single, like, measurement. It's not volume, so it's not cubed, and it's not area, so it's not squared. So it's a single measurement, so it's feet. And since it's a rate, it's per, what are we doing here? The minute. Feet per minute, 900. So it's increasing at a rate of 9 over 400 feet per minute. Okay. Cool. There goes Unit 4 review. Hopefully you guys understood all that. Almost a little tricky, so this is a good one to go back over again.